Yeah. Hello guys, I think it's time to start. Sorry for making you wait. It took a little while for me to figure out how I could, record myself. But now I'm recording myself on Zoom and I'm gonna post the recording on Piazza afterwards. So thanks for attending today's final exam review session. Yeah, I'm gonna be solving 4 to 6 questions that I think will help you to get ready for the final exam. Yeah, I'm gonna solve a couple of questions. I do want to breathe. Sorry. Nothing. Yeah, anyways. So okay, I'm gonna solve a couple of questions from practice problems, a couple of questions from homework assignments, and so on. But let's start with solving final practice problem 3, right? So we have to find an formula to find an estimate for 3 parameters, right? Lambda, mu, and p. So I'm gonna find an estimator for lambda, because since you figured out how you do the other ones, just the first one, then you can do the other ones. So a question is, how many of you want me to go over expectation maximization? If yes, please raise your hand. If no, I'm gonna directly solve the question. Okay. Okay. So I guess okay, let me do a brief review of expectation maximization, and then I'm gonna start solving the third problem of final practice. Okay. So let's say, for those who attend to my lab sections, I've already seen this like many times, but I want to iterate over again. So let's say, so yeah, let's start from the beginning. Okay, so expectation maximization is a clustering technique. It's a soft clustering technique, right? And mixture models are probabilistic way of doing soft clustering. And mixture models, every cluster represents a distribution. So let's start with this basic example. Let's say we have two clusters, and then let's say we have one-dimensional endpoints. Let's say from x1 to xn, and let's say, so cluster one belongs to distribution D with this parameter, and cluster two represents this distribution with another parameter. Okay. So if I say, so let's try to visualize this. Here is our one-dimensional line, right? And let's say we have data points on this line. So this is from x1, x2, let this be xi, all the way down to xi. Okay. So assume that we know our distributions. All known. Let's say, so let D could be any distribution. Okay. So let's say this is C1 distribution for cluster one, and this is the distribution for cluster two. So let's say you would like to find which cluster Xi belongs to. Okay. So what we will do is to look at here and look at here, right? And this point will represent this, and this one represents this. So since, oh, this must be C1, right? Okay. Since this is bigger than this one, right? Then we say that Xi belongs to cluster two. Okay. So let's try to write this more formally. So we'll say Xi belongs to cluster J star, let's say, where J star is. We have two distributions, right? One and two. We want to get the distribution that maximizes this problem. Okay. So in order to do the clustering task, right? We need to know this probability value. And this can be found by using conditional probability formula, right? Or Bayes rule. So this is this, right, times this divided by the given point. So in lecture notes, this is denoted as pi j, right? And this is denoted as gamma j. And this is the likelihood of xi, given that it's in cluster Cj. So, okay, we need to find this in order to do our clustering, right? And in order to find this, we need to find these components. Let's see how one of these look like. Okay. So let's say assume C1 represents normal distribution, right? The parameter this and this. Similarly, second one. Then this would be what? This would be basically the density of Gaussian distribution. Um, yeah, and that's this. Okay, so in order to find this, we need this, and these two are the same, right? So we need these parameters actually. We can do MLE estimate to find these parameters to plug in here and then find the other ones so that we can find this. So let's recall the MLE estimates for the MLE estimate for formula for mean and Gaussian distribution. It is this. Right. So we need the data points that belongs to C1. But if you remember, that was our goal, right? We were trying to find this, but in order to, in order to find the data points that belongs to a specific cluster, we have to do these steps, and then we reach the place that we started, right? So that's when expectation maximization algorithm becomes handy. So let me write the brief pseudocode for expectation maximization algorithm. Right. So given K, right? So um, so you have to find K next step, but for now you can assume that K is given to you, right? And let's say you have n data points, x1 to xn. So in the first step, you need to initialize all parameters, right? So we need to initialize pi1 to pi k, and we need to initialize all of the parameters of our distributions. Okay. Second step is the E step. So this is where we do the segmentation. Right. So we're gonna be finding gamma ij values. And then the third step is the M step. Right, M step is the place where we update our parameters. So we need to update these a number of parameters. And then the fourth step is we're gonna repeat step 2 and 3 until convergence. My handwriting is horrible. Sorry for that. but uh, this is not, so I assume that you already know these things, right? So let's say, so, and okay, so so in order to update our parameters, we need to use some formulas, right? And these formulas can be found by taking derivative of our Q function, right? Equalize it to zero, and then isolate this given the constraint. Yes. Okay. So this was our Q function. Copy that quickly. Yes. So this is where the question starts, right? So the question says we have three clusters, right? And then uh, let me write down the clusters. We have, so the first cluster we have is zero truncated Poisson distribution. So this is basically a Poisson distribution, but the random variable is restricted to this. So it cannot be zero. And then we have a geometric distribution. And then we have what? Borel distribution. I'm gonna be I'm gonna be finding the formula that you're gonna use in M step for the first cluster. Otherwise, it's gonna take a lot of time. So, okay. So since we know K, right, we can expand this. So we can expand this like this. Okay. So, and we want to take derivative of this in respect to what? In respect to lambda, right? So the first the first cluster is our Poisson distribution. Second one is geometric distribution, right? And the third one is going to be in terms of view. And then we have, since we have this constraint, we're gonna use Lagrange multiplier here. So we have this term, right? It's written like this. Okay. So since we are taking derivative in respect to lambda, we can, you know, uh, simplify this expression. So let's start from here. There's nothing in terms of lambda, right? So we can get rid of this. This is in terms of mu, right? So we can get rid of this too. This is in terms of p, right? And this is just pi 2, nothing related with lambda. And what we have is this at the end. Let me see what was the PMF for this distribution. Yeah, and then so the distribution is, so I'm gonna replace this probability with our PMF. Okay. So it's this. So in order to start taking derivatives, I'm gonna use these three properties, right? And in exam, we're not gonna deduct any points if you don't write these properties, but it's good practice to write them down, okay? Because I graded the first question of midterm, and I saw that many of you did a mistake using properties of logarithm. So please write these down and then move forward, okay? So we expect you to memorize these three properties, right? We know this. Okay, so I'm going to be using these three. So first, I can write this like this. So should I copy this or? And this is nothing related with lambda too, right? So we can get rid of this too. So what we left is only this times this. So uh, so I'm gonna treat this as A, treat this as B, and write it as log A minus log B. Xi is at the exponent. I'm gonna write this actually like this. Minus this. And then I'm going to treat this as A. I'm going to treat this as B. And then write it as log A plus log B. Um, So this is nothing related with lambda, right? So we can get rid of this as well. So what we left is this and this one. So let me write it. So we're gonna have, I'm gonna take derivative of this and derivative of this times gamma I1, right? Please tell me if I'm going to pass or no. Good. Okay. Yeah. Okay. So can someone tell me what's the result of this derivative? 1 over lambda, that's right, because we can set the base as e, right? So this becomes natural logarithm of lambda, and the derivative of this is 1 over lambda. Okay. Can someone tell me derivative of this?
Is it e to the lambda over e to the lambda minus 1?
Exactly. Exactly. So what you did is probably you took derivative of this, right? And then you divided it with this itself. Great. Okay. So we rewrite this. Okay. So this has nothing to do with xi, right? Similarly, this has nothing to do with xi as well. So I'm gonna take these out of the summation. So what we're gonna have is this. Okay. So my question is, do you think this equals to 1? So I want to make further simplifications before I isolate lambda and then find the formula for it. So do you think equalizing this to 1 would be a valid standard?
No.
We call that gamma ij as this. Then take a look at the description of the homework. It says these form a PMF. So given this, we just say this equals to 1. Okay. So some of you seems to say no, so I'll take it as a no, and you will be right, right? So if these form a PMF, right? So this wouldn't be equal to 1, but instead this would be equal. And we are iterating over I and not J. So this is not necessarily equals to 1. So don't do this mistake if you're gonna see this kind of example in the exam. Okay. Okay, let's move on then. So we can't do further simplifications. I'm gonna put this to other side of the equation. So instead of rewriting that, let me say this equals to 0 and these two are equal. So did you guys attempt to solve this problem on your own? And were you able to isolate lambda? No. No. Okay. So I wasn't able to isolate it as well, but and then I made few, research about it, and then it says if we put lambda over here, then and then put this over there, there's no closed form solution of this. But I realized that we can do a simple trick to find an estimate to isolate lambda. Okay, so I'm going to show you how you can do that. So what I'm going to do, I'm going to put this into here and put this into here. Okay, so this will be flipped. This divided by this thing. So I'm gonna divide both of them by e to lambda, right? So it will look like, so this thing e equals to this, right? This divided by this is e to power of lambda divided by itself minus this, right? So this is basically what? So, and notice that this grows much faster than this, right? I try to plot this function, and then it says, so it looks like this, obviously, right? My aim is to get rid of this, right? One way of doing this is to take limit of this as lambda goes to infinity, right? But I realize that we don't have to increase lambda a lot, because when lambda equals to 5, right, the corresponding y value is 0.006, something like that. So if we have, a lambda value that is not too small, that is not like 1, 2, or 3, 4, then what's going to happen is this terms will go to, will approach to 0. So what we're going to have for here is going to replace this by 1 over lambda. Yeah, so what you can do is, so I think you will know that this, this grows much faster than this, right? Because it's an exponential function, right? So I don't think we're gonna give this kind of tricky question in the exam, if you're gonna ask this kind of question. But yeah, so I don't think you need to deal with this kind of tricky stuff.
So we just need to isolate lambda, right?
Yeah, if that's the case. Okay. Yes, so what we have is this. Right. So I'll flip this. As a result, I'll have this, right? If, let's say, let's stick it on this. Any questions? And you're gonna do the exactly the same thing for two other distributions. If you don't, if guys don't have any questions, then I will move on to my next question that I prepared for you. So the sec, yes, yes.
So basically, you just have to like derivate, differentiate the three functions and isolate the lambda, mu, and p.
The parameter, yeah. That's it, yeah.
That's the answer.
So after this, after doing, taking derivative, setting equal to 0 and then isolate it, you're gonna get a formula, right? So that formula is the formula that you're gonna use to update your parameters in M step. Okay. Okay. So yes, I want to discuss about how you could, use proof by induction to prove something. We realized that so you use proof by induction in the extra credit of third written assignment, and we realized that like most of you are struggling to prove using induction, and this might be, knowing this might be helpful in exam too. So that's the thing I want to do is to solve the question, like the first part of the extra credit of third written assignment. I'm gonna show you how you can, do it using induction, and hopefully you're gonna, you're not gonna be struggling anymore. It's actually really basic, but it could get really hard if the question is tricky. But we're not gonna ask you to tricky questions in the exam, I guess. Oh, so do you guys want a recap for station distributions, Markov chains? Yes, I see a yes here. Yeah, okay. I'm gonna do a brief recap for it then. Mm, okay. So we represent, or we can represent our Markov chains. We can represent any graphs using adjacency matrices, right? And adjacency matrices hold weights. Uh, if the graph is a Markov chain, then what we're gonna have a probability values instead of weights, right? And this M is now called as transition probability matrix instead of adjacency matrix. Okay, so this is the formula for station distribution. So let's understand what this says. Okay, so you should you should you should have seen, the formula for eigenvalues, eigenvectors, like this, right? In CS1 32. In this case, this is the so if you go to if you search what's the formula for eigenvalue, eigenvector, what you're gonna see is this. Okay. And then, but normally, if the formula given in this way, then this means that this is a column vector. Right. This is a column vector. So if X is a row vector, then we can adjust this formula like this, right? In this case, this is row vector. Similarly, this. So this thing actually, looks like this, right? So there is a hidden one here. So this means that this pi is the stationary distribution of M for corresponding eigenvalue 1. Okay. So let me write this down. It's the eigenvector of M that corresponds to biggest eigenvalue, which is 1. So we can have negative valued eigenvalues. So I don't want you to, prove it or give me a, rigorous explanation, but can someone tell me why this might be the case? This is the case. Why can't we have, negative valued eigenvalues for M?
Probability constant.
Yeah, that's right. So the thing is, okay, so if we think, matrices can represent two stuff. The first thing could be the collection of data points, or could be a matrix that will transform your vector. Okay, so let me explain what I mean by that. So let's say I have a vector that is 1, 1. Okay. So we can use some, matrices and multiply with this vector and then transform this vector. So some matrices could, rotate this, some matrices could, shift this, and can do multiple kinds of, transformations. So let's see an example of this. Let's say I want to, make this bigger. So if that's the case, then I can use this kind of matrix. If I multiply this with our vector, let's say this is X, then what we're gonna have is this, right? And the result is going to be, so we're gonna multiply this with this, and then, so this is 2 by 2, right? And this is 2 by 1, and the resulting thing is going to be a vector, which is 2 by 1 vector, right? So the result is going to be this times this times this. Sum it up to similarly for this. right? So the our new matrix, I mean new vector, looks like this. So you see, you can use, different kind of matrices to transform your vectors. And what this says is there are some values, right, which are eigenvalues that could do the same transformation as A does, right? Okay. So in this case, instead of multiplying our vector with this matrix, we can simply multiply this by 2, and it will give me the same thing, right? So this means that 2 is an eigenvalue of this matrix. So let's see what happens if I multiply this with a negative value number. Let's say I multiply this by 2, then this would be -2, -2, right? So the corresponding eigenvalue would be what? -2. Okay, so as you said, if we don't have any negative values here, then this will make any, this kind of transformations. And that intuitively means that the eigenvalue shouldn't be something that, change the coordinates of this. Does this make sense? Okay, so this is an intuitive explanation of it. Yeah, so okay. So the thing is, it's not easy to find the eigenvalues and the eigenvectors, right? So in order to find the station distribution, we're using the power method. So if you look at the lecture notes, what you're gonna see is this. Please be aware that this is not transpose, right? Because we realize that some of you use this as transpose, but this is just the power of x, right? So we have given you this kind of formula. So we have transposes here. The reason is because x, so you're going to use this formula if x is a column vector, right? So a column vector, let's say it's n by 1, right? So this has to be same dimensions, n by 1, and this is our square transition matrix. We can't multiply these two, right? That's why we took transpose of this, which makes it this, right? Now we can multiply these two. If we multiply these two, then what we're gonna have is 1 by n, right? But what we want is this. So we take transpose of this two. That's why we have two transposes. But if you know that your x is a row vector, then you can basically use this formula. But you don't have to memorize it. It's like intuitive, right? If this is 1 by n, this has to be 1 by n2. This is n by n. So by doing this, check, you can validate the true formula for power method. Okay. So, and if you take limit of this as t goes to infinity, right? If this exists, then what you're gonna get is the stationary distribution. So if M is irreducible and aperiodic, right? So these doesn't make sense to you because I think these are two abstract concepts. But yeah, I think it's good for you to understand what they mean, but we don't expect you to, use the properties of, connectivity and a periodicity to do something, right? So anyways, so if n is irreducible and aperiodic, then it's guaranteed that it's gonna converge. If they're not irreducible or aperiodic, then it may need more iterations to compute this. Recall the third or the fourth homework assignment you did, right? You implemented no, in the lab assignment you implemented the vanilla power method and then the clever one. So these methods finds the stationary distribution. I can talk more on these things, but I want to move on to the question that I prepared for you. I mean, that I'm gonna solve for you. Yeah. So, but we're gonna using some of the properties here to solve the question. Let me give it. Okay. So let me copy down the question. So we have uh, MD or square row stochastic transition probability matrix, and that this be its stationary distribution. So the question asks, show that if this is the eigenvalues corresponding to eigenvalues lambda 1, lambda n. Given this, we want you to prove that same eigenvectors are also, the eigenvectors MT corresponding eigenvalues. Okay, so let me show you the steps I follow to solve a question, prove something using induction. So let's say you got this kind of problem in final exam, and this says, hint, solve this using induction, or you want to solve a question using induction, then I recommend you to follow these steps. Okay. So first, I will what I will do is to write recursive formula and then I'll do base case, and then inductor. I'm gonna be talking about these two, but let's first find a recursive formula, right? I told you that this is the standard eigenvalue vector formula, but now our eigenvectors are row vectors. So we're gonna be using this formula instead. Okay, so what's given to us? We know that these are eigenvalues of n that corresponds to these eigenvalues, right? So what's given is, so can someone write me a formula like this using or eigenvalues, eigenvectors and eigenvalues? So I want you to use these two to write this. So this is our eigenvector, this is our eigenvalue, right?
So like you can do eigenvector times m is equal to lambda times the vector.
That's right. Basically, right? If this is our eigenvector, if this is our eigenvalue, then I'm just gonna plug in these values here. What I will have is this. Okay, this is given part, right? And what we want to show is so we said then show that these are the eigenvectors of this that correspond to these eigenvalues, right? So what this means is so or A is now empty, right? Our eigenvalue is lambda E, and then this is our eigenvector. So this is what I meant by a recursive formula. Why this is recursive? Because I can write this like this. And then I can rewrite this as, 1 times n to the power of e minus 1 and so on. So this has a recursive structure. So, okay, we found our recursive formula. Now we have to deal with the base case. So what we're gonna do is we're gonna plug in now, so 1 for t, because this is the smallest value that he can take. It could take 0 as well, but that would make our matrix null. So I instead start with t equals to 1. So I'm gonna use, this. I'm gonna use my recursive formula in each step, in each case. I'm gonna start with one side and try to reach the other side. Okay. So if I plug 1 for t, I will have this. Right. Since power is 1, I can just erase it, right? And this is actually the given part, right? So this is already given to us. So we actually prove this. Okay. Now we have to do the inductive case. It's the most important part. So what we're gonna do is we're gonna plug in t plus 1 for t. So normally t is not equal to t plus 1, but this means that we're gonna put t plus 1 every time we see t. Okay. So inductive case, what you're gonna do, you're gonna assume that this is true, right? So we're gonna use our recursive formula, which was this. And this is true. And we need to show that this is also true. And show that questions, you're gonna pick a side, left-hand side or right-hand side, doesn't matter. But you have to pick one side, start from there and try to reach the other side. Yeah.
How do you know that you have been something better?
I just so okay. So the thing is you can treat it as a column vector as well. But in the homework question, right? This question was given in homework, right? VA3. And if you look at the first question, we have given that's the first question is also about station distribution, right? And then we have given, this formula. And this implies that station distribution is row vector, right? And since every eigenvector is a candidate of a station distribution, I could just assume that, it's row vector, but you can do it. You can treat it as column vector too. Just for the convention. Okay, so I want to pick this side. I'm gonna start from this side and try to reach here. While doing this, I'm gonna be using this and or base case. So this is what you're gonna do. You're gonna pick a side, try to, rewrite it like this as the other side of the equation. While doing this, you're gonna use your recursive formula and inductive, base case. Okay, so long story short, we can write this like this. So we already know that, okay. So actually, I'm gonna do this. So we know that we can rewrite this like this, right? So what I'm gonna have is this.
Right. I'm saying,
times them. Great. Catch. So, and then what I can do, I can, use the base case to write this equal or base case, right? This equals to this. So I can write this as lambda I times EI, and this will be +1. And we're able to start from here and reach to this side. Okay. Any questions? Make sure that you're comfortable with using, proving using induction. If you follow these steps, then you're gonna be fine, I think. So do you guys wanna give a break, 5 minutes break, or do you want me to continue? I can continue. Okay. Nice. Yeah, so my third question. So I'm gonna be solving questions as much as I can do. I'm a little bit sick, so if I get tired, I'm gonna stop. But I'm gonna stop. I'm gonna, I won't finish before solving 4 questions I prepared for you, and I'm gonna start solving questions from practice problems, and also when we all get tired. Okay. So my third question is about metrics. I think this is an important topic for final exam. So let's recall what metrics are. Okay. So let's say we have two data points, x1 and x2, and they look like this. So let's say this is our x1, which is this, let this be our x2, which is this. So I want to compare my two data points, right? So I might want to, compare two data points to see if they look alike, if they're similar or not. So one way of doing this is to, find the distance between these two data points. So how would you find the distance between these two data points using, elementary algebra? Yeah, we can use norm. So we learned in the high school, in the elementary school, I learned to, find this distance between these 2 points as like the difference of x right squared and then difference of y squared. That would be what? So this is 4, this is 1, and we make this 5. Okay, so as you said, this is actually can be found using Euclidean norm. So we can, so this is Euclidean norm, right? But we can use also Hamming distance as well, which is the first norm of this difference. But what if I want to compare, let's say, so we might not have, vectors or, multidimensional data points that are like, these are called vectors also, but anyways. So what if I want to compare, let's say, sets, graphs, and other kinds of data structures? So I'm gonna be showing, so let's focus on graphs, right? Can someone recall me what kind of, distance function we can use to find distance between two graphs? So in this case, for vectors, we use norms. We have seen a distance metric for comparing graphs, and I'm asking you what that was. Distance, yeah. This to find distance between two graphs. That's my question. Hmm? No, Markov chain is a data structure of representing a graph. Series? What? Taylor series. No, Taylor series are, series to approximate a function. Yeah.
Finding like the number of edges, like one graph or not another graph.
Yeah, that one, yeah. So, these are called representatives of graphs, right? So do you guys recall this? So let's say I have G1, G2, and the distance of this. So if you recall the first written assignment, given you this kind of distance function, right? So this is one way of calculating distance between two graphs. We know that norms are metrics. Let's try to figure out if this is a metric or not. So can someone recall me the criteria for metrics? So first one is about negativity. So what about negativity? Could be negative? Cannot be negative, right? So it means that point two data points, the distance cannot be negative. Okay. Second one is isolation, you're right. So it's defined as isolation says that if two data points are the same, then the distance should be zero.
Triangle inequality.
Triangle inequality, that's right too. But before doing that, there was one more. I'm gonna write that one too. Yeah. Symmetry, that's right. That means each pair is equals to this. Right, the distance shouldn't differ if I go from here to here, or if I go from here to here, right? It should be the same. This is what symmetry implies. And then the fourth one is, as you said, triangle inequality. And this is the big final boss that you have to beat. You wanted to prove that your distance function is a metric. And the hardest one among these four. So, and let me write that down too. Okay. So if our distance function satisfies all of them, then we can say that that distance function is a metric. So let's, look at each criteria and see if this distance function is a metric. Any thoughts? Do you think that's a metric? It's hard to say, by just looking at it, but any ideas? Yeah. It seems like, right? You're gonna see that it's actually a metric. But let's prove that mathematically. Okay. Let's start with non-negativity. So the first three are trivial, but still I'm gonna show it. And if we ask you to prove that a distance function is a metric, you have to, show all of them. So let's say we have G1, G2. We're gonna use the definition. So we're summing this with this. So this thing is what? So absolute value, no. Yes, cardinality, right? So these are sets. So we're just finding the size of these sets. Cardinality slash size. So we know that a size of something cannot be negative. It could be zero. It could be, something positive, but it can't be something negative because we can have negative sizes, right? So this is bigger than or equal to zero. bigger than or equal to zero. If we sum these two such things, then what we gonna get?
I have a question.
Yeah,
So two, that sign is different, right?
this is set difference, yes. So if this is bigger than this one, then what you're gonna have is an empty set. And the cardinality of empty set is going to be zero. Okay, we prove the non-negativity. Let's look at isolation. So notice that we have if and only if statement here. That means that you have to prove both sides, meaning you're gonna, treat that you have this, and then you're gonna try to show that x and y equal to each other. Once you prove that, you're gonna start from that side and then show the other side. Bless you. Okay, so let's do the first part. Uh, Given that so we're gonna use the definition again. So we know that this equals to zero. In order this to be zero, right? So both have to be zero, because let's say if this is positive, then this has to be negative, right? In order this to equal to zero. And we know that we showed that cardinality cannot be, it's cannot be negative. So both of them should equal to zero. If they both equal to zero, that means that E1 and E2 are the same. That implies that our graphs are the same. Okay. So we're gonna do the opposite, right? We're gonna start with this and then reach to this place. Given if G1. So this is pretty straightforward, right? Uh, I can write G1 for G2, and then I'm gonna be like this. Since these two are equal to each other, it's going to be 0, 0, 0. So we show that our distance function equals to 0. Okay, so we're done with the isolation part 2. Let's look at the symmetry part. So we have to show that so we can say this. I'm not gonna write it down. I'm just gonna be showing it here. So since if distance of G1 and G2 is this, right? And then distance of G2 and G1 is the same, but you flip these two. Because summation is commutative, you can just flip it. It's going to be the same thing. And then you're gonna say that due to commutativity of summation, this holds, right? So let's deal with the triangle inequality. Okay, so triangle. Triangle inequality says distance between G1 and G2 must be smaller than distance between G1, G2, I mean G3 plus. Okay, we're gonna use the definition. Rather view quickly. Should be smaller than this. Plus. Plus. So in show that questions, as I always say, you have to pick a side, start from there, and then try to reach the other side, right? So what I'm gonna do is I want to pick this side. I'm gonna be doing something on this, and I will try to reach to this place. Okay. So it's actually enough to show that so Mhm. So it's enough for me to show one of these because this is this says the same thing as this says, right? So basically, I got this part, and then I got the corresponding, elements for this. Similarly, I did the same thing for this one, right? So if we show either of them, then it will be enough. So I pick this thing, and I'm gonna prove this, and we're gonna be done, you know, showing this inequality. Does it make sense? So instead of like dealing with this one and with this one, I'm just gonna deal one of them, and that will be so. And the procedure I'm gonna apply will be the same for this one. So I don't wanna deal with, both of them. So I'm just picking one, and do my computation. Let's do this. start with this. So any ideas how we could start from here and try to reach this place? So what we have on the right hand side is E3, right? So we have something E3, but we just have E1 and E2 here. So we have to incorporate E3 here, right? So my hint would be, let's say, I have this, okay, x plus 5.
Add in the bracket three.
Yeah, so what I'm gonna do is something like that. But I have to plug in, I have to sum E3 to here, but without, violating this inequality. So let me give you my hint. As you said, so I want you to, let's say we have x plus 5. I want you to write this in terms of what you will do is, okay, we'll say I could write it as 3 plus 2. So I'm gonna be, doing the same thing. So I'm gonna be looking at, so this implies that this expression can be, break down so that I can write 2. So I'm gonna look at how can I, visualize this so that I can incorporate E3. So let's try to visualize this. So these E1, E2, E3 are sets. Right. So here's E1, and I am subtracting E1. I'm subtracting E2 from E1, right? So the corresponding place will be where? Or E2. This will be my E1 minus E2. So I can, let's say this is triangle. I can write this as how you could, okay, I'm gonna ask you this instead of directly showing you that. How I could write triangle using E1, E2, and E3. Yeah, so what I'm trying to do is to, try to, try to write this thing in terms of E3. So, and this represents this region, right? And what I want you to do is to maybe, find a way so that you can write this using
Can you
E3.
use substitution here?
Substitution. Yeah, you can use set difference. Force substitution.
From the first equation, the top equation, you can like isolate like the set to each side and like this whole equation, then you can substitute it in terms of its frequency.
Oh, I see. I see. Okay.
Will that work?
That will make things complicated, I guess. Yeah. So you said E1 difference E2. That's right. Okay. So let's see. So if we subtract E2 from E1, what we're gonna have this, and then you want to union that with this side. So that will be here, right? But do you want this region as well? So you're missing this region.
But how do you know that this Venn diagram will always be the case?
Yeah, so okay, so the thing is, so okay, so what you're saying is E1 could be equal to E2, right? Or E3 could be equal to 1. So how we are
Any
asking
other configuration?
any other configuration, right? So you're right, actually, but so these are special cases of this, right? So an expression that you will, find using that configuration will be equal to an expression using this one. This is the generic case. The other ones are the special cases of this general case. So anyways, yeah. Okay, so what I will do is, so I'll try to rewrite E1, okay, in terms of E1, E2, and E3. I mean, sorry, I'm gonna try to write E1 in terms of E3. So that's how I did it. So I'm trying to, I'm trying to rewrite this place using E1 and E2. And that you can do this like this. I'm gonna skip this part fast because it's almost 9, but I can help you if this confuses you. Okay. So if I plug in this value here, right, then what I gotta have expression in terms of E1, E2, and E3. So let me write E1. Okay. So recall that we're trying to show this, right? Now, what we have is E1, E2, E3, right? So, what I'm gonna do, I'm gonna distribute this here and to here. This. Yeah. Let's go. Okay. So let's see what steps could we take so that this will look like this more, right? So what we have is so we have this and this, right? And this thing looks like this almost, right? So what I want to do is I want to get rid of this thing, okay, so that this will look like more like this. Any ideas how I could get rid of E2 here? So my hint is, notice that we have an inequality sign here, but we haven't used any inequality signs, right? So maybe I can write something that is bigger than this. Yeah, that's right. That's right. So if E2 is an empty set, then subtracting it wouldn't make any difference, right? If it is not, if this is not empty set, then this thing is going to be smaller than inequality without this. So I'm gonna do what you said. I'm gonna use an inequality sign to get rid of E2. So let me copy down here so that you're gonna take clever steps. By the way, no, I didn't. Write this. So I'll just get rid of this. So recall that. Yeah, we call it like this. Is also known. So what I will do is I'm gonna treat this part as A, treat this part as B, and I'm going to write it as C. So this looks great because we achieved to, show that one part looks like this. Now we will try to show that we will try to, modify this so that we're gonna have something like this. Okay. So one good way of, approaching this side is to distribute this again. Well, difference E2 intersection. So. Yes. What do you think we should do? So we want to write this in terms of like something that we want to modify this so that it looks like this, right? E3 set difference E2. We have E3 set difference E2 over here, but this is unwanted, right? So we want to get rid of this part so that it will look like this, and we're gonna be done. Yeah,
They could do inequality. It's the intersection.
that's right. That's right. So intersection, if we just get rid of this, right? Intersection will make things the same or smaller. So if we just get rid of this, then right, this will be this thing will be bigger than this thing here. So let's say, as an intuitive example, I have this. Let's say this is this is this, and intersection of it will be what? Will be just 5, right? So intersection just makes things smaller, or if we don't have something common, let's say 11, then what we're gonna have is empty set, right? So we can safely say that we can just get rid of this. And this is the part that we're trying to reach. So we all show the 4 parts. And we showed that this distance function is a metric. Yes, so it's been 2 hours. So if you guys are tired, we can stop here, or I can continue solving, some questions. Depends on you. You're done. Okay.
Thank you.
Bye-bye. You're down. If nobody wants, then I will stop it. So please give me an answer. Yeah.
Can I get a reading?
Yeah. On what?
The written.
Taking assignment. Okay. Which one?
The last one.
Last one for which question? Page rank. Oh, second one or the first one? First one. Okay. I'm gonna look at it. Tonight. Okay.
Very request that I start credit to the professor.
Yeah.